Dear students, I welcome you to this EPG Pathshala and myself GS Meena. Today we are going to discuss on the module membrane processing in food processing under the paper principles of food processing and preservation. In this module, you are going to learn about the basic difference between the membrane processing as well as classical processes. So you can say that there are different number of ways in which we can separate or process the uh, this feed or separate different things. So here we are going to learn about the classical difference, that what is the membrane processing and what is the other conventional processes. We will also learn about the different generations of the membranes, that how this has been evolved, and we will also learn about the different types of membrane modules. So membrane module is something that how we are going to fix a particular membrane in a particular module. So how we are fixing it, that is known as membrane module. And we will also learn the important application of this membrane processing in different food applications, like you can say it may be production of beer, it may be production of wine, it may be production of this vinegar, it may be production of fruit juices, and it is having different other applications in dairy industry, and now it is having a emerging market in the production of functional food and nutraceuticals, and all these things we are going to discuss in this particular module. Moreover, we are going to learn about the application of membrane processing in the vegetable oil processing and dairy, which is a early adapter of this membrane processing. So we are going to learn so many things in this module. Hence, the objective will be like we will learn about classical membranes, their types, design, and difference between dead end filtration and cross flow filtration. Moreover, which are the membrane generation which has been available in this market, and we also learn the potential application of membranes in processing in different fields, like food processing, which includes like in the this wine and beer production, in vinegar production, in fruit juices and beverages in dairy industry, as well as in the this nutraceutical and functional food markets. Among the wide range of the available separation processes, membrane technology is defined as a broad term that contains several separation processes on molecular level. That is, membrane separation usually applied on the molecules which are having size less than 10 micron, while classical separation is used for the size of the molecules that are having greater than 10 micron. It is among the vital fields of food science. A set of specialized equipments is used for a particular membrane process that enable it to show its typical separation characteristics as well as make it suitable for specific desired single or multiple applications. Water industry, that include drinking water plus wastewater processing and water desalination, has the largest commercial market for membranes worldwide. In last 20 to 25 years, the market volume of different membranes has increased about 800 to 850 millions euros in food industries, and the same is now stand as the second largest commercial market for membrane on global basis after the water industry. Moreover, about 20 to 30% of the total membrane production in use in food industries, that is annually increasing at the rate of 7.5% in this sector on global basis. Membrane separation is performed above the atmospheric pressure, that is varies with particular membrane process in a closed system. So these processes are termed as or known as pressure driven membrane processes. For membrane processes in their ascending pore diameter are reverse osmosis, that is RO, nanofiltration, that is NF, ultrafiltration, that is UF, and microfiltration, that is MF, are mainly used in food processing. UF systems as well as UF membranes have the maximum share, that is 35% in global membrane market, followed by the share of MF systems and membranes, that is 33%. NF and RO combinedly have market share of 30%. Membrane contactors, electrodialysis, and pervaporation are the other membrane processes what contribute only 2% in the total membrane market. Classical membranes, their types and design. Membranes are semi-permeable barriers used to separate two phases which restrict the transport of various substances in permeate and retentate streams in a specific way. That is, the separation will be on the basis of particle size, shape, electrical charge, etc. The separation efficiency of a particular membrane is usually affected by different processing factors like fluid composition, pH of the medium, temperature, applied pressure in the membrane, feed flow, as well as interaction between feed component and membrane surface. During membrane processing, a particular membrane material is fixed in a particular membrane module, that is platen frame or spiral wound, hollow fiber or tubular, and operated within prefixed operating conditions to perform assigned tasks. Membrane process were initially operated in dead end filtration module, that is shown in figure 1, in which feed stream was subjected to membrane that retains the bigger size molecules in retentate and allow the smaller molecules to pass and permeate. That is also single stream. The main problem of such systems is the rapid cake layer formation over the membrane surface, which is directly responsible for membrane flux reduction, as it is shown in figure 1b. This problem was overcome in cross flow design, in which single feed stream is subjected to membrane parallel to its surface in closed system at higher pressure with turbulent flow that divide the feed into two streams, namely permeate molecules which have passed through the membrane and retentate in which the membrane has been retentate the molecules. The turbulent flow helps in reduction of cake layer formation through continuous sweeping action of suspended particles over the membrane surface that results in better flux than dead end filtration over the higher length of time. In this figure, first we will see, that is on the left side of this figure, that A, particularly dead end filtration, in which we can see that the feed is entering over the this membrane or the filter surface, and the retentate will be retained over the membrane surface and permeate will go out, as it is shown by this arrow at the bottom. If we see its flux versus time curve, then we can see that the flux is decreasing continuously from higher to lower end, and the cake layer thickness is increasing, or we can say vice versa is also true, means when the cake layer is increasing, the membrane flux is decreasing. Now we will take the second case, the cross flow operation, in which there are three streams. First feed is going there and permeate is coming out, and retentate is continuously sweeping by the turbulent flow which is applied in this membrane processing. As a result of this turbulent flow, the cake layer thickness will increase, but not in the same manner as it is increasing in the case of dead end operation, and that is results in the reduction flux but at a lower rate. It means the flux in the continuous flow operation will be higher always than the dead end operation. Moreover, this cross flow filtration, this is the main basis of this membrane processing, is always conducted in a closed environment, while dead end filtration or operation is always may be conducted in open atmosphere pressure. So in this case, membrane processing always done in a closed system. Membrane generations. As per the technical development carried out till date, membrane materials can be classified in 4 generations. First generation, cellulose estate derived membranes, which were developed to desalinate seawater. They were susceptible to microorganisms and disinfectants, as well as sensitive to pH and temperature. In such membranes, the applicable pH range was 3 to 8, and maximum temperature which this type of membrane can tolerate is 50 degrees centigrade. A second generation membrane derived from synthetic polymers like polysulfone, and these membranes are better than the first generation membranes, as having better resistance toward hydrolysis, pH and temperature, but have lower resistance to mechanical compactive. This generation of membrane contain around 200 different polymer material. Coming to the third generation of the membranes, mineral membranes consisting ceramic material based on zirconium or aluminum oxide are usually deposited on a graphite surface. These membranes have great mechanical strength, are chemically inert, and can be operated on high pressure, wide pH range, that is 0 to 14, it means complete pH range, and the temperature was, these membranes can be subjected to temperature greater than 400 degrees centigrade, although such temperatures are not applicable in dairy and food industry. Their main demerits of these membranes is their cost. These membranes are very expensive, then first generation and second generation membrane, but the same is compensated by their long operation life. So it is clear that if we want to use a membrane material which can be long last, then we need to opt mineral membrane. They are costly, but their life is quite long. Fourth generation, these contains hybrid process, that is the combination of conventional electrodialysis and different pore size membranes like electrodialysis combined with MF, UF, NF. The continuous electrophoresis with porous membrane is defined as an electrochemical process to separate charged organic molecules utilizing electric field as a driving force. Under the effect of an electric current, ions are transported from one solution to another through one or more semi-permeable porous membrane. Now we will discuss about the membrane in food processing. So availability of few food materials in their naturally pure form underlines the importance of different separation and purification processes in transforming food or feed substance into safe and direct consumable form. We can see that we are producing lot of foodstuffs, but they are not in the natural form. So we have to apply one or another kind of process by which we can make them eatable or suitable for the direct consumption. So for selected applications, this membrane processing is a superior and conventional method owing to its inherent advantage, such as like lower energy consumption, fewer and mild processing steps, generation of this greater separation efficiency, improved final product quality. That is very important, because if you are producing a product and it is of not a quality product, then it is not any significant. Eco-friendly, because it is not harshing or harshing the environment. And cleaner processing. Cleaner processing means better quality product at lowest cost with highest environmental protection through minimum or low waste generation. So that is the reason this membrane processing is preferred a lot. Nowadays, these processes has been become an integral part of different industries like functional food industry and nutraceutical. Both industry are has significant impact with the health, and agriculture, dairy, and byproduct industries. Membrane application in beer, wine, and vinegar production. Currently, membranes are being used in this area for clarification of beer, wine, and vinegar, as well as dealcoholization of beer. In the classical beer production process, details are given by Lipinski 2010 as an alternate to reverse osmosis is used for the beer dealcoholization prior to its clarification by microfiltration before pasteurization and bottling. Closed flow membrane, particularly MF, is used to recover beer from the yeast beer mixture that is settled on the fermentation tank bottom, and also to concentrate yeast. The membrane system's investment is usually compensated by the beer recovery. Moreover, MF now successfully employed for beer clarification, that is, for removal of yeast, microorganisms, and haze without adversely affecting its sensorial attributes. RO is used to tailor the alcohol content in beer to produce alcohol-free or reduced alcohol, that is 8 to 10 times less alcohol content beer without affecting its flavor. It is carried out in 4 steps. It means beer is pre-concentrated in the permeate that contains water plus alcohol, and retentate concentrated beer plus flavor, followed by diafiltration of the permeate and tailoring of alcohol content as per the desired taste using desalted and deoxygenized water. Post-treatment, which includes the addition of hoops and syrups in alcohol, tailored beer to compensate the taste losses arise from the loss of taste carrier alcohols. These steps are performed at the temperature lesser than 7 degrees centigrade that results in a production of improved quality beer rather than the conventional process. Reverse osmosis is used for the must correction or rejuvenation and dealcoholization of wine, while MF UF is used for the wine clarification during wine manufacture. If you want to go in details, please refer this Lipinski 2010 reference. Must correction or must composition is balanced with the help of reverse osmosis, which increases sugar content in wine through concentration and at the same time enhances tannins and organoleptic components by 5 to 20%. It is an efficient method to maintain the quality of must obtained from these grapes harvesting during rain which are having moisture content, but the same is less effective in maintaining the quality of must made from the grapes of stale maturity due to cold weather. The use of this particular method is depends on the regulation of various countries. During wine clarification, MF and UF provides an alternative to the classical fining substances filters and also reduces the number of processing steps. Lipinski 2010 reported that 0.20 to 0.50 micron and 0.45 to 0.65 micron pore size MF membrane are usually used during the filtration of white and red wines respectively. It means for white wines we are using the MF system equipped with 0.2 to 0.5 micron pore size membrane, and for red wines we are using 0.45 to 0.65 micron membranes. Rejuvenation of older wines is normally done through RO process, which removes the water, alcohol and other substances responsible for adverse aroma, followed by the addition of mineral free water during diafiltration process. Alcohol content of the wines is also tailored in the same manner as discussed above for the beer. Clarification of vinegar employing UF not only provides a wider vinegar range with same sensorial attributes without turbidity, but also reduces number of operations and reduces the storage time. Membrane application in fruit juice and beverage production. MF and UF are the economic and efficient alternatives to the classical filtration methods available for clarification of different juices. The use of membrane processing in beverage industry have several inherent advantages like improved product quality, reduced cost of production, better working environment, cleaner production with less waste generation, and improved product safety. Casano 2010 reported several merits of membrane processes over classical beverages or fruit juice refining agents, such as reduced energy consumption and cost, reduction of different filtration aids, mild thermal treatment that safeguard the product against thermal degradation, easier process and compact equipment design, fewer wastes, reduced chemicals requirements, and enhanced productivity in the range of 96 to 98%. It means when we are using membrane process, the productivity will be enhanced in the range of 96 to 98%. Moreover, fruit juice clarification with MF and UF have great potential of cost saving. If we take an example that if we are having a UF plant and its capacity is 250 meter cube of juice per day, and it is producing on an annual production basis, then it is able to reduce 79% cost than a conventional plant on the annual basis, on the yearly basis. It has been adapted from Casano 2010. So in the left corner we can see here the processing method, which include decanting, dead end filtration, centrifugation and microfiltration. Operating time, and we can see fibers retention, sensory and nutritional quality of the product, and operating cost. So if we take example of decanting, then its operating time is very long and fibers are poor. Sensory and nutritional quality in this process is also poor, and operating cost comes in the intermediate range. Then compared to dead end and centrifugation and microfiltration process, if we take the example of dead end filtration, then its operating time is long, as we have already learned that when we are using dead end filtration, the cake layer formation will take place and that will reduce the flux. Fibers will be higher. Again, sensory quality will be similar to the decanting process, and operating cost also similar to the decanting. Centrifugation process, operating time is very short, fibers are poor, and sensory and nutritional quality of the product will be high, and at the same time operating cost will be high. Now we take the example of microfiltration, or you can say that if we are comparing these four processes, decanting, dead end filtration, centrifugation and microfiltration, then operating time for microfiltration is short, fibers retention is high, sensory and nutritional quality of the product is high, and operating cost is low. So this is one of the process which is having low operating cost but having better sensory and nutritional quality, as well as this operating time is short. So MF that contains pore size in the range of 0.05 to 10 micron is resembles classical coarse filtration employed to filter juice in fibrous enriched pulp in retentate, as well as microbes free this clarified fraction in permeate. Moreover, it is known as cold sterilization process. Note it please That microfiltration is known as cold sterilization process. UF membrane is the alternate of the fining step used in classical method. It is a wider membrane pores than MF, yet retains the bacteria, fats, proteins, and colloids, but allow to pass the smaller molecules like vitamin, minerals, and sugars. Prior to UF process, both pre and enzyme treatment of the juice is essential for better yield, high capacity, and excellent product quality. Juice are first concentrated in RO, which decreases the moisture content to its half value but retains major amount of sugar, that is 98 to 99%, and volatile flavors, that is in the range 80 to 90% in the retented, having 20 to 25 degree bricks. So we can say that that is the this concentration of the solutes is 20 to 25 bricks, and at the same time it is concentrated to greater than 75 degree bricks in classical evaporation. This combination results in 60 to 75% saving of energy than traditional evaporation process. A detailed review on membrane processing of fruit juices and beverages has been already published by Girard and Fukumoto in year 2000. Now we are going to learn about membrane application in functional food and nutraceutical. So first we should know what is the functional food and what is the nutraceuticals. So functional food is the food that is defined as that the food containing medicinal value or health benefits beyond its basic nutrition, that is known as functional food, while nutraceuticals are the foods that is containing the key ingredients of the functional foods, but that is we are consuming either in the this powder form or in the capsule form. So key ingredients is normally converted into powder form, that is in the nutraceuticals. The future recently evolved bioactive molecules and nutraceutical ingredients is usually decided by the separation ability and efficiency with the retention of desired characteristics like biological activity of these ingredients by the employed separation process with the minimum inputs, which includes like energy plus capital plus labor cost. So all these costs are coming in the inputs, so there should be minimum, although a number of challenges has to be overcome to raise the concentration of a target in the end products, because it's initially in very less quantity the raw material from its raw material, yet several methods are doing this task successfully, and various membrane processes alone. We can use single membrane can do this, and sometimes we have to use combination of different membranes like MF plus UF plus RO. So different membranes in alone or in combination are used to produce numerous nutraceutical and bioactive substances from, it may be from lipid derived, it may be from carbohydrate derived, or it may be from protein derived. So protein based sources. Various membrane processes alone or in combination are used to produce numerous nutraceuticals and bioactive substances from lipids, carbohydrates, and proteins based sources. Moreover, this technology offers many key advantages during processing of such ingredients, which includes elimination of the classical evaporation that reduces their activity and high energy consuming, reduces overall water needs by reutilizing wastewater, enhances profit by formation of new products, and needs lesser floor space and investment. Table 2 represent the various applications of membrane processing in different classical processes as in several bioactives. So if we see in the table 2, then different processes has been given here. Systems, membrane system which are being used are given, and remarks is given that what is their current status. So if we see that like ultra pure water or water softening, in this RO and UF both the processes are used, and what is the remarks, what is the situation of these processes, that it's classical, it means it is well established. If effluents, so RO, NF and UF is used for the effluent treatment, and this is also well established. Fine chemical processes in which NF and UF processes are used, and they are developing rapidly. Then milk whey and milk bioactives, so in these RO, NF and UF are used, and these are also almost classical, it means developed, or some of the area like this bioactives, milk based bioactive harvesting is developing. Extract concentration, then RO and NF is used, restricted due to the complexity of the process. Emulsion separation, in this UF and MF are used, classical but also expensive. Caustic recovery. So in this normally ceramic membranes are used. Remember please that ceramic membranes are having applicability between the wider pH range 0 to 14. So it can be used then first generation or second generation membrane. So good technology for caustic recovery for all industries. Fruit juice clarification, normally MF is used and it is having established market. Oil water separation, UF and RO works well for non-emulsified mixtures. Then enzyme recovery, so enzyme is also like proteins. So UF and NF can be used for their recovery, or this pharmaceutical industries have established but growing market. Wastewater recovery, in this NF and RO used. These are commercial system and still developing. Bioactive recovery from fruit and vegetable juices and herbs and botanicals. So in this NF and RO may be used, and these technologies having a good potential. Improve beverage stability, that is another application in which MF is used, and it has good application that eliminates heat treatment better. Flavor retention is the result of this technology. Membrane application in vegetable oil processing. Traditional oil refining methods have several demerits like nutrient loss, needs higher amount of energy, water and chemicals, greater losses of natural or neutral oil, as well as the generation of more effluent. Vegetable oil refining employing membranes has been not only reported as an easier and simpler process, but also the same offer different advantages like better nutrient retention, reduced demand of energy and added chemicals, milder process parameters, and cleaner production. Because in this we are not using the traditionally used the different chemicals which are used for the refining of the vegetable oil. Several researchers have been used membrane process for the recovery of solvents from the micelle, like degumming, for blanching, for deacidification, as well as for hydrolysis of fats and oils. For detailed information on membrane application in vegetable oil processing, please see the review which is published by Cothino and co-workers in 2009. Now we will discuss about the membrane application in dairy processing. So dairy industry is a narrow part of the food processing, or you can say dairy industry is a narrow part of food processing. Moreover, this dairy industry is the early adopter of this membrane processing. It has greatly benefited by membranes as a number of applications like removal of water concentration, means we are removing water from the milk, and we are concentrating the milk solids. Liquid as well as solid liquid separations are routinely performed. If we see the potential application or the commercial application of different membrane plants in membrane processes in dairy, then we can start with microfiltration. So microfiltration, we are knowing that it is the membrane which is operated, this process is normally operated at lowest pressure and having more or widest pore size. So it is commercially used for the fractionation of the proteins. Like if we are using 0.2 or 0.5 micron membrane, then it will be able to separate casein and whey proteins. Another application that it is able to remove fat. So if we are passing whole milk through the membrane filtration, that is particularly through the microfiltration process, then it will retain the fat in the retentate and other things will be passed in the permeate. Moreover, it is also known as cold sterilization process, because when we are subjecting milk to the microfiltration process, it retains around 99.9% microorganism. So likewise, it is known as cold sterilization process, and it is being used for the this production of extended shelf life milk, which is having a better shelf life than the pasteurized milk. Another is that this microfiltration is used to separate somatic cells. So when we are these somatic cells are coming in the milk, and it will be just remove the somatic cell when we are treating milk with the microfiltration. Next process is ultrafiltration, and ultrafiltration is the process which is most widely used in the dairy industry. And if we go as per the membrane material, that which material is used, then normally polysulfone is the membrane material that is highly used, and normally the temperature of ultrafiltration is kept 50 degrees centigrade to get better flux And if we are going to some specific applications, like suppose we want to remove calcium from the ultrafiltration during the ultrafiltration from the milk, then we are reducing the temperature, and it should be less than 10 degrees centigrade, so that the calcium solubility is higher at lower temperature. If we are going by the application, then we are using this ultrafiltration foam protein standardization for the manufacturing of cheese and high protein milks. We are going for the this production of concentrated powders like WPC, WPI, MPC, MPI, and it is also used for the quality improvement of set fermented dairy products through ultrafiltration, because when we are adding this ultrafiltered retentate or skim milk concentrate into the milk, then due to the increased protein percentage in that milk, that fermented product, their firmness will increase, and the problem of waste synergy, that the typical problem in the yogurt or curd or dahi particularly, that will be solved out. If we see a nanofiltration, then it is used for the demineralizer purpose. We can produce different powders with reduced minerals. Moreover, this RO that is used for the concentration purpose is mainly used for the increasing TS in the skim milk from around 9 or 10% to 25 to 28%, and this is one of the most economical process for the removal of butter. From 1960, the major milestone in membrane development and their application in dairy processing is presented in table 3. So just have a look on this table 3. It is showing milestone in the development of membrane technology and its application in the dairy processes or the dairy industry. So year-wise developments has been given in this, and then the concerned application in the dairy industry has been also highlighted. So if we see the year 1960, so what was that time happening in the world? That at that time manufacturer was interested to develop the reproducible membranes. Coming to the 1970s, materials with improved chemical resistance was required or desired. Earlier that time they are having only materials like cellulose acetate, which is the first generation membrane material, and we are knowing that what is the limitations of this first generation membrane material. So they shifted themselves to polysulfone. So first design of the sanitary modules was carried out during this particular time of 1960 to 1970, and the application design of whey pre-treatment to prevent membrane fouling. Another development was the processes for the UF of acid whey. They have ultra filtered the acid whey during that particular time, and also developed the first UF based cheese manufacturer process, though they utilized ultrafiltration process for the manufacturing in cheese during the 1970s, because cheese is the one of the widely used product. In 1980s, improvement of membrane systems hardwares, and its hardware means like module designs, spacers and anti-telescoping devices. Another development of the commercial inorganic ceramic membranes, that is the third generation membranes. So it carried out in the 1980s. So using UF and RO membranes to concentrate milk on farm. They used RO membranes to concentrate the milk at the farm level, so that most of the water will be removed and this bulk will be reduced. Another application was defatting of whey, WPI manufacturing. WPI means whey protein isolate. It's a powder that contains more than 90% protein on the dry matter basis, and recovery of minor compounds. Separation of beta lactoglobulin and alpha lactalbumin, that was also carried out in this duration, and desalting of whey with loose RO, that is the reverse osmosis process. Coming to the 1990s, so improvement of hydrodynamics of the MF membranes, then porosity gradient membranes. Next is the control of particles deposition, vibration, rotating discs, rings, vortex and static mixers, and functionalized membranes like ion exchange. That was the development of 1990s, and these developments were frequently used for removing spores from cheese milk and whey. So this is done by the help of microfiltration, that is also known as cold slicer process. Defatting of whey, same, it can be done with the help of microfiltration. Separating casein micelles from milk, so this is also done by the microfiltration process. This microfiltration process is able to remove microorganism, fat as well as caseins, what the membrane pore size is different. Next is the extending milk shelf life, that is ESL milk. So this is also done with the help of microfiltration process, in which the membrane pore size was 1.4 micron. So when we are using microfiltration membrane, that is having 1.4 micron pore size, that is able to retain all the fat and the bacteria, and this retentage is subjected to heat treatment and added to the permeate. So this combined product is next filled aseptically, and that is having shelf life greater than the normal pasteurized milk or normal this MF treated milk. This product is known as extended shelf life milk. Next application was fractionation of the hydrolysates using the UF-NF membranes. Membrane application in dairy processing. So all four classical membrane process with their membrane pore size, application, separation mechanism, material from which these membranes were developed, along with the modular configuration, and the developed dairy waste products are shown in this table 4. So in this table 4, if we see the left side corner, here this under pore size of these four membrane process has been mentioned. So MF is having pore size greater than 0.1 micron, while UF is having pore size in the range of 1 to 500 nanometer. NF is having pore size in the range of 0.1 to 1 nanometer, while RO is having lesser than 0.1 nanometer. So we can clearly see that pore size is increasing from bottom to top, or we can see that the MF is having widest pore size while RO is having narrowest or the smallest pore size. Separation mechanism, if we see, so MF is based on sieving, while UF and NF separation mechanism is based on sieving and charge, and in the case of RO it is based on sieving and diffusion. Operating pressure, if we see in there these for these processes, then which is mentioned in the megapascal. So in the case of MF, the pressure range, applied pressure range is 0.1 to 0.2. For UF it is 0.1 to 1, and NF it is 1.5 to 3 megapascal, and for RO it is 3 to 5 megapascal. So here, as the pore size of the membrane is reducing, the applied pressure is increasing. That is the reason that MF is having the lowest applied pressure of 0.1 to 0.2 megapascal, while the RO is having the highest pressure, that is 3 to 5 megapascal. Membrane materials, and all these membrane processes are inorganic polymer membranes, which includes like cellulose, acetate, polysulfone, polyamide, and inorganic ceramic, carbon supported zirconium oxide, and stainless steel. If we see the modular configuration, then these are having tubular, multi-channel, hollow fiber, spiral bound, patent frame, these configurations. So there are 4 types of configurations which are mainly used for the membrane processing, that is spiral bound, hollow fiber, tubular, plate and frame. Separation domain. So MF is mainly used for the somatic cell, bacteria, fat globule, and casein micelle separation, and the product which are available in the commercial market are micelle casein and native whey proteins. UF is normally used to separate soluble protein as well as caseinomacropeptide. So UF is known as the concentration process for the proteins, and it is used to manufacture whey protein concentrate, whey protein isolate, milk protein concentrate, milk protein isolate, and beta lactoglobulin and alpha lactalbumin. Nanofiltration, that is also known as loose RO process, it is particularly used for the indigenous peptide salts, it means particularly divalent salt separation, and it is used to produce bioactive milk and whey proteins hydrolysates and GMP. RO is normally used as a concentration process, and it removes salts as well as water from the permeate from the feed, and it is used to produce lactose, concentration of whey permeate, or delactosed deproteinized whey. Figure 3 is showing application of membrane technology in milk processing. So various applications of the 4 present different classical membrane processes are showing in this figure 3. In order to reduce concentration, polarization, and fouling on the membrane surface, distribution membrane flux, usually skim milk is used. That's why skim milk is normally fed to the different types of the membrane processes, because it is having less fat, and that is results in the better flux and less fouling. Or you can say vice versa is also true, that if fat is less, membrane fouling will be lesser, and we will be able to get the better flux. In this figure, if we see the left corner, then concentration of this skim milk with the help of UF, MF, and diafiltration. Then what we will get? We are concentrating skim milk with the help of UF first. So it will be giving us the retentate which is very high in the milk proteins. So if you further want to increase the protein content of this retentate, it may be up to 20% or 21 or 22% in the retentate. The protein percent in the retentate will be around 21 to 23%. So if we want to further increase this, then we need to go for the diafiltration. And diafiltration is nothing what we are doing, that we are having UF plant and we are adding a certain quantity of the water into the retentate. It means the feed side, and we are removing the same quantity of the water from the that product or the retentate. So it is diluting the retentate solids, and the dissolved solids will be further passed through the membrane. Likewise, it is increasing the concentration of the proteins. So finally, we will be getting this milk protein concentrate in the range of 80, 85, and 90. Next, fractionation by MF. So it is again depends on the membrane of MF. So if we are using 0.1 to 0.5 micron membrane, then we are able to separate whey proteins and casein. So micellar casein solution is added to the cheese milk that is used for the cheese manufacturing, while the whey protein solution, which is going in the permeate side, that will be concentrated by UF, and it is used for the production of whey protein concentrate. Then we can apply ion exchange and chromatography, and we can use we can produce lactoferrin, alpha lactalbumin, and beta lactoglobulin. Then standardization by the UF. This skim milk is standardized with the help of ultrafiltration process, and the protein content is standardized particularly, and it is used for the manufacturing of either cheeses, different type of cheeses, or the high protein milk. Then concentration of this skim milk by RO, and it will reduce the TS of this skim milk up to around 25 to 28%. If we are using skim milk, then the TS of skim milk will be raised from its normal this total solids around 8 to 9% to 25% to 28%. And this is one of the most energy efficient method for the concentration. Such retentate is used in the ice cream manufacturing. So here in this figure we can see the application of membrane technology in whey processing. In the previous slide we have seen the membrane application in skim milk processing, but in this we are going to see that which are the different application of membrane processing for the utilization of whey, which is a byproduct of different ingredients or products, like you can say cheese is the most important commodity from which the highest amount of whey is generating, as well as paneer, chena, caseins, as well as the co-precipitates. So from all these this whey is coming out, and it is one of the major challenging tasks because it is having different problems for the utilization. Earlier it was normally said that it's the waste, but nowadays it is known as gold. So the concept has been totally changed now, and all the credit is goes to the membrane processing, which has been created new avenues for the whey utilization. And earlier it was just known as that it is throwing in the gutter, or it was throwing in the farms, which is again a alarming thing, because this pollution will be severe in the environment. That's why this all the environment protection agencies are not allowing that. So ultimate, what should be done with the huge quantity of whey? So membrane processing was adopted by the dairy industry, and this membrane processing has been enabled the dairy industry to convert this whey into the value added products. And now a number of, or you can say an array of different products has been converted from this whey to give the new product to the consumers, and that's why it is now known as liquid gold in the dairy industry, whey particularly. So whey first pre-treated with the microfiltration. When we are pre-treating with the help of microfiltration, it means we are defatting it as well as we are sterilizing it. All the microbes, 99.9% microbes will be retained. Then it is subjected to demineralization with the help of nanofiltration. We are knowing that nanofiltration is a loose RO process which is removing all the minerals and water. Then it will be dried and we will get the partially demineralized whey protein concentrates. In the second stage, if we are concentrating with the help of ultrafiltration, then we can produce whey protein concentrate. If we are using this UF permeate, and if we are demineralizing it with the help of nanofiltration, then the partially demineralized permeate will be concentrated in the RO, and it is crystallized followed by drying, and we will get the good quality lactose. We are also knowing that how the lactose is produced. So whey is a source of lactose production. If we are giving heat treatment and we are fractionating by MF, then we can fractionate phospholipids from the whey also. Defeated whey will be again concentrated with the help of ultrafiltration, and again the permeate will be going for nanofiltration followed by RO, and we are getting the lactose. Otherwise we can we can get defeated whey protein concentrate or in the powder form also. If we are going for the this polymerization, then fractionation by MF, and we will get beta lactoglobulin, purification by UFDF, and we will get pure beta lactoglobulin. Solubilization, then we are going for the purification by UF, pure alpha lactalbumin. So by which we can produce different products. Nowadays different biopeptides are being generated with the help of microfiltration. It is used as a very emerging field in which these membranes are used to convert this whey as a base to the novel dairy ingredients, which are having very high demand in the market due to their physicochemical or functional or physiological or medicinal. And now say you can say that due to the nutraceutical values of these products. Now we are going to conclude this session, that what we have learned in this particular session. So in this module we have learned about different membrane process, namely microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. All four pressure driven membrane process which have major use in food processing. Classical membranes, their types and design, followed by the dead end filtration, cross flow filtration. So we have learned that cross flow filtration is better than the dead end filtration, and the different membrane generations. So till now normally 3 generations, but the 4th generation of membrane is in the market, that is the hybrid membrane. So moreover, superiority of the membrane in cross flow filtration over dead end filtration has been explained, that results in energy saving during membrane processing, and that is the basis for this whole membranes. So important application of membrane in different processes, like in the production of beer and wine and vinegar, as well as fruit juice and beverage manufacture. Membrane application in the oil processing, and its application in the production and purification of functional foods and nutraceuticals is also discussed. So membrane application also having significant role in vegetable oil processing, uh, as well as the higher side use of membrane in the dairy industry, particularly in the processing of skim milk as well as processing of whey, has been explained in this particular module. Dear students, I thank you for your keen interest in this e-module. I hope it is fulfill your desired, and you have benefited in a better way. Thank you.